Okay, so the net change theorem just says that if you want to know how much something has changed, if you know the rate, so the net change is equal to the integral of the rate, whatever. So let's go ahead and do that with this thing here. Let's see, it says that we have the volume of the balloon changes from this to this in a time Net change in the radius of the balloon. Okay, so we need the volume formula. Volume is going to be 4/3 pi r cubed. That's the volume of a sphere. And this is confusing. How do we do this? Let's see, between time find the net change in the radius of the balloon during that time. Okay, so essentially I want to know the rate at which the radius is changing. I want to know this thing. Okay. So let's see. Okay, so I think I was just overthinking this. I think I'll have to check with the book. I took this from the book. This is just, it's almost too simple in the sense that the net change in the radius is just the difference between the starting radius and the ending radius. So we don't need this calculus stuff. This is, we can push this aside, shrink it down, put it down here. We'll use it maybe later. Hopefully we'll get to use it in a bit. But for this one, I think all we need is to find the initial radius and the ending radius. So start radius. Let's see, this is going to be 36 pi is 4/3 pi r cubed. I hope this thing, this works out. Look at this. This is 27 is r cubed. So r is equal to 3. So it starts out at 3, and then the ending r is going to be, let's see, 288 pi is 4/3 pi r cubed. So what does this mean? I may actually have to work this one out. 144, 72 times 3. So r cubed is whatever 72 times 3 is 216. All right, that works. Okay, so r here is 6. Okay, so net change in radius, it goes from 3 to 6. The answer is 3. That one was boring. We didn't get to use calculus. Let's use calculus. Hopefully this one does. Otherwise, I'm going to have to go hunt up some more of these and then make a new video. Okay, a particle moves in a straight line with acceleration. Okay. Velocity and displacement. Okay, so at time t and the total distance traveled. This one's going to be a pain. Okay, so this one we can use this net change theorem for sure, because we're going to start off, we have our acceleration, and we want to figure out the velocity. So let's see, v of t is the integral of a of t. Let's see, up to time t equals 6. Well, let's actually just get our functions. That's probably the easiest thing to do. So v of t is going to be the integral of t minus 3. And that's going to be t squared over 2 minus 3t plus some constant. What's the constant? Well, v of 0 is equal to 3. And so that means that 3 should equal 0 over 2 minus 3 times 0. So 3 is equal to c. So my v is going to be t squared over 2 minus 3t plus 3. Okay, now we can actually use the net change theorem. I mean, I guess that we're really using that for, yeah, I guess I really did use that, you know. Maybe I should write it that way. Here, let me write it. Let me do this second time. We'll get the same thing, but you'll actually see that I'm using the theorem. Okay, so velocity is going to be the integral from, let's see, starting at 3, ending at x, let's call, whatever, t, of the rate. So now I'm going to have to change variables. There we go. So this is the net change in velocity, and that is the starting point. So that's essentially how this shook out, is that we actually just did that, and it's kind of all masked, if you will. Oh, sorry, not from 3, from 0. Had 3 on my brain, because the starting points are given at 0. Okay, so we'll do this. I'll do it the right way for the position, this d distance. So d, we want to know t equals, so d of 6 is going to be the integral from 0 to 6 of the velocity plus d of 0 So this is going to be, let's see, t cubed over 6, 3t squared over 2 plus 3t. This all evaluated from t equals 0 to t equals 6. D of 0, where we're told, was 0. So we're good there. So this is going to be, let's see, 216 over, it's 36. And then 3 halves of 36. 1850, 54. Plus 3 times 6. That's just 18. Wow, that works out to be 0. Interesting. So, so this is really interesting that the total displacement, the displacement is 0. So you end where you started. So this particle is ending at t equals 6 is at the same place where it started. Now let's figure out how far it moved, because it can move. If you can imagine a particle, where's my? No, I don't want to do that. No, don't show that again. I was pressing the wrong thing. This is what I wanted. Okay, let me let that go. So we have this particle, it starts here, it moves over here, and then it moves back. It might end where it started, but has moved quite a distance. So what we're going to have to do is we're going to have to figure out how far it's traveled. Well, the way we're going to do this is we'll find out where is v of t equal to 0. And so where was v of t? V of t is right there. So let's see, t squared minus 6t plus 6 equals 0. Does that factor? Of course it does not. Drat. T equals negative. So I'm going to use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, 36 minus 24 is 12. So here's what we're looking at, which is 3 plus or minus radical 2. Lovely. Okay, so if you had a timeline, so this is t equals 0, t equals 6. Unfortunately, both of these numbers are here in this range. So you start this particle moving at t equals 0, and I don't know if it's going up or down, I don't care, but it stops at t equals 3 minus radical 2 and turns around, starts moving the opposite direction, and then it stops again at 3 plus radical 2 and turns around again. So we need to know the positions at each of these points. Oh man, I picked a doozy, didn't I? So here's how I would do this, is I would compute d of 0, d of 3 minus radical 2, d of 3 plus radical 2, and d of 6. And then I would figure out how far it's moved. And I'm just going to pause this video so I can do that calculations off. Okay, so some of you probably noticed I made a mistake right here when I went from this step to this step. This wasn't 3 plus or minus radical 2, it's 3 plus or minus radical 3. Some of you have no idea how I got that, so I might as well show you. This is 3 times 2, of course, is 6, plus or minus. 12 is 4 times 3, so that'll be 2. Radical 3, pull the 4, separate that out, and then you can cancel the factor out a 2. And those cancel, so there it is. So I blew it, there, fixed. Then I computed, and I was interested to see that the D they were nice numbers, sort of. It depends on, beauty's in the eye of the beholder. Okay, so now we see how far we've traveled. From here to here, we've moved radical 3. From here to here, we've gone 2 radical 3. This is the total distance. Total distance. And then from here to here, I've gone radical 3. So let's see, that's a total is 4 radical 3. All right, hope this helps.